All right, so we're right on the verge of finishing up benefit cost analysis, and the very next section of the course, the very next module is pollution policy. And so I want to wrap up today. I want to wrap up uh, benefit cost analysis. I want to give you guys a little bit of practice, just working through a simple benefit cost analysis problem where you have to add up benefits and costs over time, given certain parameters, given certain uh, costs and benefits, and different time profiles associated with each. Um, give you some practice just with a simple example of that, and then it's going to relate to a pollution policy topic, which will kind of I'm hoping that today's class will kind of build a bridge between benefit cost analysis, which we've just come out of, and then the pollution policy stuff that's coming up, where we'll talk about different options for dealing with pollution, different policy options, different ways of approaching the problem, different ways of regulating it, either through strict technology mandates or standards on each individual source, or perhaps allowing flexibility through some kind of tax schedule for a certain amount of tax per unit of emissions discharged, or a permit scheme. We'll talk about different ways of regulating pollution in the next module. And so for today, what I want to do is just go over some of the mechanics of benefit cost. Just remind you of some of the concepts that we had gone over. You begin by just listing off all the relevant benefits and costs that you can think of, both the ones that you can monetize, and as well as the ones that maybe you can't. You want to enumerate those and make a list. The next step is to use some of the non-market valuation techniques or the market valuation techniques, depending on whether the costs and benefits can be monetized. If the goods have direct prices in markets, you can use those. If they don't, if there's something like clean air or public nature area that doesn't have you don't pay for all the benefits you get from it. You don't pay for getting to go up and go for a hike, or you don't pay for going to a lake and taking a canoe on the lake, because it's a public resource, so there's no monetary goods. But we talked about some ways that could be potentially valued in terms of either a travel cost model or a contingent valuation survey. So to the extent you can, you want to then monetize those values. Figure out when they're going to accrue. Are they going to accrue right now, or next year, or the year after that, or are they going to accrue for the next 20 years each year? You want to account for the time profile, and then you want to make some summary. You want to have some summary number, which in some cases there's a couple different ways you can do this. One is you can think about net benefits, which is benefits minus costs. And in particular, you'd want to find the present value of benefits and subtract the present value of cost. If for example, these benefits and costs are not just single numbers in a given year, but there may be a flow of benefits or costs over time, then you'd want to discount those in the years that they happen, discount them back to the present, and then add them up once you've done that. Another way to do it would be to think about the ratio of the two of those two things. That would be either benefits over costs, or if you have a flow of benefits and costs over time, you'd maybe do PV benefits over PV costs. The ratio will tell you, in a sense, what the rate of return is on the investment. So given the fact that you get some benefits out of it, what's the extra benefits you get relative to the costs, as in a ratio form, which is sort of almost like a percent. You can almost calculate a percent return, like a return on an investment. And so if you get a high number here, something greater than 1, that would be good. That means you're getting more benefits per unit of cost. If this difference here is greater than 0 up here for net benefits, that means that you have more benefits than costs. So those are just two ways of expressing it, and depending on the scenario, you might prefer one or the other, but it's not always the case that one is better than the other. They're it's useful to calculate both and to consider both when you're thinking about what to do. So just as an example of this, like, so here's what I mean by when I'm taking this part here, this step that I'm doing here between B minus C and PV B minus C, let me be a little bit more explicit of what that looks like. So what that involves is I'm going to have benefits listed over here on the left, and costs, costs are over here on the right, and I'm going to denote the time period by this is time. This index on the left is time. So for each of these benefits and costs, they occur at different points in time, and if you want to discount them, if you want to calculate the present value, you need to divide them by 1 plus r, where r is the discount rate. If you need to divide each of those by 1 plus r, that will take them from future terms into present terms. Once you make that discount, once you divide by 1 plus r or 1 plus r squared or 1 plus r cubed, depending on if you're talking about years 1, 2, or 3, once you make that adjustment, once you divide by 1 plus r to some power, that will bring all those values back to present values. And once they're in present values, then it's valid to add them up because they're in the same terms. It's almost like these are in different units. It's almost like these year 2 values, these year 1 values are in different units than the year 0 values. And when you discount them, you sort of transform them into the same units as the year 0 units. Because having dollars today, it's not exactly equivalent to having a promise of some dollar value in the future. So this is like just an example of the mechanics of this. So we have, just in this simple case, we have $1 of benefits every year for year 0 through 3. We discount each of those. There's $2 of costs every year. Those get discounted, and then you'd sum those up down the column essentially, and you'd get you get total present value benefits on the left and total present value of costs on the right, and that's a more explicit version of this formula that I wrote down here on the previous sheet. And in this case, we can see that costs are greater than the benefits every single year. So it's pretty clear that this would be if this is a 4-year project where there's benefits immediately, and then a year later, and then a year later, and then a year after that, and those benefits and costs had this exact profile, then we would know this is not a viable project. It's not a project that's returning more benefits than the resources that it requires. However, if we had a different profile here, if say benefits accrued every single year, maybe they were $1 every year, but maybe costs were something like this, where you paid the cost immediately, you paid like a $2 cost immediately, but then the costs in all subsequent years were 0, right? Then we'd have a different story. Then we'd have to actually, in that case, we'd have to know what the discount rate is in order to actually figure out whether that's a good idea or not, because this would be $2 of costs in present value terms. This would be a 2 down here, and the present value benefits is at least $1, and then depending on what the discount rate is, these subsequent values are going to be deflated by some amount. So if that's extremely steep, in theory, you could have a total on the left-hand side here that's less than $2 if that discount rate is extremely high. If the discount rate is low, then it's likely that your benefits are going to exceed the costs. So overall, this is kind of the formula that's in the book. You have some summation, benefits in year T minus costs in year T. Actually, that's a little bit different than what I had just done on the previous slide was more like this. Starting at 0 and summing up to T, minus the same thing for costs. So you might see this written out in kind of a tighter set of notation with this sigma notation. This is This is a sigma. This is a Greek letter, capital sigma. And that just means you're gonna take all the values at each individual t, compute the value at each t, and then add them up over all the t. In this case, it's starting at t equals 0, going up to the terminal time, whatever the end date is for the project that you're evaluating. In our previous slide, it was 3. So in the previous slide, this would be a 3 up here at the top. But it in general, you can have any kind of length of time horizon that you want. And let me just say, there's one last trick that is important. It's a mathematical result, which it's not central to understanding the economics or central to understanding the concepts of benefit cost analysis, but practically this is a very useful trick. Practically these two mathematical results are very convenient to have on hand. And I went over one of these at the end of last class. I told you that if you have an infinite sum, if you have something that goes that starts with 1 over 1 plus r, and then the next term is 1 over 1 plus r squared, and the next term is 1 over 1 plus r cubed, and if that just keeps, if this exponent keeps increasing by 1 each time, and it goes on forever, if that sum never ends, if that's an infinite sum, you end up with 1 over r. That's a result that's a mathematical result which is applied a lot in finance. I could show you the proof. If you want to see the proof, I can show you in office hours sometime if you're curious as to why that's true. But the important thing is just to note that this will collapse. That entire sum, like an accordion, it's just going to collapse down to one single number given by 1 plus r. If this isn't a 1, in the numerator, let's say this is just some value v. Let's say this is just some value. Then you just have a whatever number that is goes in the numerator on the right hand side. So that works as long as the numerator is the same for all of those terms. Then you'll get that entire infinite sum to collapse to something that's a much easier to express just in a single term. And then there's a variation of this, which is a little bit not as tightly expressed. It's not as simple of an expression, but it's very useful when you're dealing with things that are not infinite. When you just have like a series that starts at time 1 and then ends at some terminal time t, and that's given by this second part down here. So this is the same as the one on top, except it stops. It stops at time t rather than going on to infinity. So this is the same as what's on top, except for the fact that there's this extra term on the right. You still have 1 plus r on the left, but you have 1 over 1 minus 1 plus r to the negative t on the right. It's a little bit more complicated, but ultimately it's something that you can compute. And so there's another way of expressing this. This is like this, just to show you a different way of writing this. That's an equivalent way of writing this expression: 1 over r times the quantity 1 minus 1 over 1 plus r to the t. So that's another result that it's very useful to know if you have, let's say you have a 30-year project, and you know that some aspect of the costs or benefits is going to be the same every year in years 1 through 30. Then you can take that value. If it's a cost, let's say that value is c. If you have c every year, then you just multiply c by that expression, 1 over r times 1 minus 1 over 1 plus r to the t. And if it's a 30-year project, if that c accrues over every year for 30 years, then that t becomes 30, and you have a nice tight way of calculating the present value of that stream of costs. And when it works equivalently for benefits, any value you can substitute in for c there, as long as it's the same value in every year. If the value changes over time, then it doesn't collapse like that. Then you would have to calculate that out completely. But if it's the same value, then it's a nice tight expression. Okay, so I have made available a problem, an in-class problem that I wrote on Friday and Saturday. This will be in-class problem 6. You can find it on Moodle. I made it available. It should be visible to everybody on Moodle. Here's the problem. Okay, so this is going to be a pollution control problem. There's two sources of pollution. One of the sources emits 4 tons of pollution per year. Another source emits 6 tons of pollution per year. The 4-ton source has a way of mitigating its pollution or completely eliminating its pollution with a $3 investment in the first period. And then once it, you can think of that as like installation costs. So it has to install some kind of technology or install some new equipment. That costs $3 right up front. Once that's installed, however, it only costs $1 every year to operate. So the costs have some upfront component and then some variable component over time. That's for one of the sources of pollution. Okay, the second source is it's a bit larger of a polluter. It's got 6 tons per year, and its pollution reduction process doesn't involve any upfront investment. There's no initial investment. It's just a cost of $1.75 per year to completely eliminate the 6 tons of pollution. Okay. Now, the benefits of this are going to be given by the willingness to pay of the population that's surrounding these two sources, or the population that's affected by these two sources. And I just defined a simple willingness to pay function given by this table of numbers here, where if there's no reduction, that has no benefits. There's no additional benefits of having no reduction of pollution. If 4 tons are reduced, the total willingness to pay for that pollution reduction is $1.80. If there's an additional 2 tons reduced and a total of 6 tons reduced, that's has an aggregate value, a total willingness to pay of $2.50 among those affected. And then if 10 tons are reduced, that's a value of $3.30 on an annual basis. These willingness to pay values are per year. So the pollution would be taking place per year, and pollution reduction would be taking place per year, and the benefits and the willingness to pay to have that reduced would also be accruing every single year, because you have value on not breathing in the pollution each year that you don't have to breathe in the pollution. So this is going to have a 10-year time horizon. So this gets a little bit tricky, but I explained it as best I could here in writing, where you have the present is year 0, kind of like what we just looked at on a couple slides ago. The present is year 0. That's when the investment would take place. So if source B, for example, is wanting to invest, they're doing that in year 0, and then it becomes effective in year 1. Year 1 would be the first year in which the pollution is actually reduced, and that's when the benefits of the pollution control would be realized. That's also when the operating costs would have to be spent. So the time horizon we're thinking about is years 0 through 10. 0 you can think of as the present. That's going to be undiscounted, but anything after year 0, year 1, 2, 3, 4, or 5, up through 10, that's going to have to be discounted. I realized I did forget to specify the discount rate. Use a discount rate of 4%. I think I forgot to write that down on these instructions. So just consider the discount rate to be 4% per year, and then calculate the benefits and costs for these different pollution control scenarios over the whole time horizon, time 0 up through time 10. Okay, so the first problem here is going to ask you to find what the benefits, like the present value of the net benefits for just controlling source C. The second problem is going to have you consider the present value of net benefits for just controlling source B. Question 3 is going to have you look at it if both, we'll look at the net benefits, the present value of net benefits, if both sources control their pollution. And then based on that, you should be able to find some level of control that maximizes the net benefits, and that's what we would define as the efficient level of pollution. So that's what the fourth question is asking there. Point number 4, or question number 4. I've just sketched out on my screen here just a little bit of perhaps a template that you might want to use for keeping track of your values. You have, year 0. That's going to be a one time period in which some costs are going to occur, especially for the source that has the investment. And then really the years 1 through 10 are all going to be kind of the same value. So you can kind of consider the period 1 through 10 as like almost like a distinct period, almost like one single period, where the future benefits and costs are going to occur, and you can use this this formula to kind of collapse those values into one value, collapse those values into a single present value for the stream of benefits and costs that occur over that time period. Okay, so the first one here is what is the present value of net benefits of controlling pollution for 10 years just at source C? Okay, so this is for source C. We have 6 tons. We have 6 tons of emissions that we could potentially reduce. We have a abatement cost or a reduction cost of $1.75 per year. So for number 1, that's the 6 ton source with $1.75 abatement costs. So this would be no initial cost. So year 0 has no costs, but the cost in years 1 through 10 is going to be $1.75 per year, and we would divide that by, I guess we would take this formula down here and bring that up. 175 is the yearly value. That's the value that is occurring in year 1, year 2, year 3, and up through year 10. So that's the value that goes in the numerator of the first term. You divide that by you divide that by 0.04, because our discount rate is 4%, and then we would just compute this value. We take 1.04, we'd raise that to the -10. We would subtract that amount from 1, and then we'd multiply that by this $1.75 over 0.04. That would represent the present value of the cost of reducing pollution through just source C. Okay, so that's the costs, and then the benefits. We're looking for the present value of net benefits. So that's the cost side. The benefit side is that we reduce 6 tons of pollution per year starting in year 1. So that's a value. If we look at this table of willingness to pay values, 6 tons reduced per year. The value of that, the total value of that in the economy or to the population that's affected is $2.50 per year. That would be a similar kind of calculation, $2.50, I believe. You divide that by 0.04 in the same way that we did the other quantity. We'd multiply that 1 by 1 minus 1 plus. I guess we could shorten that up. We could just say 1.04, raise that to the -10, and that would represent our total benefits, our present value of benefits of reducing pollution in that amount. So either we could, so we could compute that out. Either we could take the benefit value and subtract the cost value. Alternatively, one way that we could do this is, instead of computing those out separately with multiplying it by that big term, we could actually just combine this together, change the term that's outside of this large term, change this to $2.50 minus 175, and divide that whole thing by 0.04, and then multiply that by this term on the right. That would be an equivalent way of doing it, because we know that the benefits every year are $2.50. The costs every year are $1.75. So those are going to accrue in years 1 through 10. Those are going to be constant, and those are going to be the same in years 1 through 10. And so you take that and divide that by 0.04, multiply that by the term on the right, which sort of helps to collapse that number into a present value. For the second one, we have a similar scenario, although it's only, let's see, the second one is source B, if I remember right, and that's 4 tons of pollution per year, which has a willingness to pay for those. That 4-ton reduction is not $2.50, but instead that's $1.80. And then in this case, it's a $3 upfront cost. So this cost in the beginning would be $3, and then the subsequent costs would only be $1. And so you'd have benefits equal to something like this. You'd have costs equal to 3. That's in the present. That's in year 0. So that's just a 3. There's no discounting that's required because that's immediate. That's happening right now. And then there's an additional cost of one per year for years 1 through 10. And so that's something like this. Okay. And then for the third question, it's gonna, in some ways, it's gonna combine just what you did in the first two, but there's a little bit of a wrinkle, and that wrinkle comes in with the fact that you can't just take the net benefits separately and add them together, because does anyone see why that doesn't work, to just strictly add up the net benefits of what you get in 1 and add those to the net benefits in 2? Does anyone see why that wouldn't give you the correct value for number 3? Just taking a straight up sum of 1 and 2.
Is it because there's a different willingness to pay for when there's 10 tons of pollution reduced per year than there is from just adding like 4 tons reduced and 6?
Yeah, exactly. So the fact that the willingness to pay at 10 is not just a linear combination of 4 and 6. It's not just the sum of the previous 2. It's like a diminishing relationship where the extra benefit of going all the way to 10 after you've already gone to 6, for example. Notice the marginal benefit from going from 6 to 10 is only 80 cents. But whereas the marginal benefit of 4 tons going from 0 to 4 is $1.80. So that's more than double the marginal benefits when you're starting at 0 and going to 4, as opposed to when you're starting at 6 and going up to 10. You'd have to take so your total benefits in that case would be 3.3. You'd swap in 3.3 for the 1.8. That would be the total benefits of 10 tons. You'd still have the costs of source 2. So you'd still have this. You can actually you'd still be able to keep this part there, but you'd have to then include the costs of the other source, which was $1.75 per year. And so that's something like that. So does anybody was anybody able to get the value for 3? One trick that I used to get this value here was just to take 3.3 minus 1 minus 1.75, use that as the term out front, because those benefits and costs are all occurring in the same every year from years 1 through 10. And so that would sort of be the variable benefits and the variable costs, and then you just have to subtract 3 from that quantity to account for the initial investment costs, which are occurring in the very first time period. Yep. And then so exactly, 1.46 is or 1.461. Yep, is the number that I got for 3. Yep. The efficient level is the level at which the gap between benefits and costs are as wide as possible. So we talked about this before a little bit in the microeconomics. We want to find the point where this gap is largest. What that actually is, mathematically, that's where the net benefits are highest. which are the things that you calculated in one, two, and three for the different levels or the different ways of getting pollution reduced. So you would just be looking for whichever is highest.